So now we'll move on to something called the normal approximation to binomial. And I'll start by going on to Desmos. And having a look at the first a binomial distribution, and I'll give it NP. And then I'll do a normal, and I'll give it a mean of NP, and hopefully you're seeing how that's the mean of the binomial distribution, and then root of NP 1 minus P for standard deviation. And notice as I move the probability of further away from 0.5, the distributions match less well. And if I expand this and stretch this out a bit, if I now start increasing this in like this and make n really large, it becomes closer and closer, but as I make n smaller, it becomes less of a good approximation. So that's why when n becomes really big and it becomes a bit hard to do, and like say we've got an n of 286, we wanted to figure out probability of less than 100 successes, we'd have to add up 100 different probabilities with really large combinations which calculators sometimes can't handle. So there's got to be a better way. And there is something called an approximation. Now, there are some conditions for an approximation to be used. We calculate the mean and variance of the binomial distribution and then pretty much use it to calculate a normal distribution. But there are a few conditions. For example, NP must be greater than 5, and n times 1 minus p must also be greater than 5. And anyway, so those are the conditions. But if it says use a suitable approximation, that tells you conditions are already met. So the first thing you do is you work out your new parameters. Mu equals NP, which is 0.3 times 125 here. This is your N, this is your P. So 37.5. And then you need to work out your standard deviation, which is root of NP on minus P, which is 0.3 times 0.7 times 125. So that's root of 105 over 4, which is root 105 over 2. Now, here's the thing. When we're going from discrete to continuous, and so that means if we just do less than 46 here, and we try to do that on the normal, we would be leaving out values that actually round to 46, because 46.45, that rounds to 46. So we must account for that using something called a continuity correction. And so here it's saying more than 45. And we need to think, okay, if we want it to be more than 45, we want it to round to 46 at least. So then we just want it to be greater or equal to 45.5. And if it was x is less than 45, we would do x is strictly less than 44.5. X is less than or equal to 45. It can be 45, so we just do x is less than 45.5. And if we want x is greater or equal to 45, well, it can be 45, so we'll do back to 44.5 again. And then again, as I said before, 4 out of 5 would be x is greater or equal to 45.5. And remember, the greater and equal to, or the strictly equal to, or strictly less or greater than, it doesn't matter because it's continuous. But I like to be a bit pedantic about that. So now we've done that continuity correction, so we do a z. We've standardised 45.5, and then we subtract our mean, which is 37.5, and we divide by our standard deviation, which is root 105 over 2. And then this would get us 16, I think, over root 105. And then this would this is 1.56123 dp. Now then we go get our table. .561, so 0.947. Oh, and remember, because we're doing greater than, we'd have to do 0. Like that.